All right, so welcome to Unit 5. If you made it this far, it's all downhill from here. This section is much easier than the last two that you've done, so it's very quick, but I'm starting here in my little space because it's just a topic to talk about again. I'm going to talk about sampling. I've talked about it here and there, but now I'm going to go through like a more like what's in the book and stuff. So, right, we talk about inferential statistics. I keep saying inferential statistics, right? We infer knowledge on the for the population, for the general public, from a small sample, right? So we infer something. If you've taken English 1D by any chance, you know all about inference, right? Anyway, so inferential statistics is what we use from samples to generalize to a bigger population, okay? And so when we're talking about a population, we're talking about like anything. We can define it, the population of the planet, the population of the United States, the population of Delta College. When I say the population and I say the population of Delta College, I'm talking about every human being. I'm not talking, so, right? There's the population of Delta College, which includes all the staff, all the students, all the workers, everybody, as opposed to the population, the student body of Delta College, which would just include the students, right? So whatever it is, I can just define it as that's my population. And so then it's not realistic to study populations. Logistically, getting in touch with people, it's just extremely challenging. So that's why you always see surveys, polls, especially during the selections, right? You just know that there was a lot of surveys and polls done. And those are just groups of people. They're across the country, of course, right? They don't ask everybody in the United States. They get a group of people, a sample. So samples is how we get statistics, right? Statistics are what we get, what we call the data we get from samples. Okay? And samples don't always provide the true picture of the population, right? It could be wrong. We could, for a variety of reasons, it may not, the knowledge that we're trying to generalize may not be true, right? Right? The sample, for a variety of reasons, which we'll talk about, may not truly represent the population, right? And right, but we still need to use samples because financially, logistically, the feasibility of studying populations is just not there, right? Even if I wanted to study, even if I wanted to just study, if I decided the population was the class, right? If we were in person in class and I just said, we're going to use this and you're the population, chances are there's somebody absent from the class. So I still wouldn't be able, if I defined it as the census from the class, I still wouldn't be able to do that because that particular time somebody would be absent. Right. So even on that smaller level, trying to get a population is challenging, right? So it's always about samples. And then one of the great reasons that the sample may not represent the population we're talking about is because of bias, right? So there's things that happen, and when we're talking about bias, what we really mean is we didn't take a random sample. Everybody did not have the same chance of being placed in the sample from the population. So out of a population, when we want to take a sample, we want to make sure that everybody in that population, as whatever we defined it, has the equal opportunity to be part of the sample. Hope that makes sense. All right. One of the big, so where's like the most bias lie? So if I have a sample of what we call a sample of convenience, right? So if I said, if I chose all you guys, who's ever left who's ever in this class, and now say you're the sample I'm going to use to represent the student population of Delta College, right? That's because it's convenient for me. You're here. I can talk. I can get the information, right? I can do the survey or whatever it is I'm looking to do. But that's just convenient for me. It does not mean you at any level truly represent the makeup of the student population, right? So it's convenient, but it does not. It's really not a valid sample, right? Right, and that's how we get what we call sampling errors, right? So there's a lot of things that happen during this process of getting a sample that creates errors. And sampling error is what the null hypothesis always said. If we come up with a difference between the means, then the reason is sampling error. Because if theoretically, if we studied the entire population, we'd have the nice bell curve and there'd be no difference between the means. Those theoretical models, right? And that's how it explains it away, that we made a mistake. Somewhere along the line, the sample was an error, okay? So you would think some things like you might logically think, seem reasonable is that the more people you have, the better off you are. That is only true to a certain extent, right? So if I choose 3,000 people to be in a sample and then I say, oh, I need more people, and I just add 100 people, that's really not going to make a big effect, right? If I doubled the size, that would have more of an impact, right? But if I just add 100 people, or if I add a small 1% on top of whatever it is my population, it's not really going to make a difference, right? So sometimes it has a minimal impact, but you need to have a large enough sample to really do a proper representation. And no, we have no formula for what that number is. Sorry, or maybe you're not sorry. The more closely related your sample people are, like the more similar the people in the population are, the smaller the sample you need, right? Because the people are very different from each other, then they're all going to be. It's easy to project from a small sample to the population. However, if there's a lot of variability between the members of the population, then you need a larger sample to get a true representation. Yeah. No. So then we have what we call quota sampling, which is really basically just that. Like I'm going to pick a number of people. I'm going to pause this for a minute because I have to pull something up. All right. So sorry, I had to find this, right? So this table of random numbers is in with your tables and syllabus, in the syllabus tables, etc. module, and this is in the packet of tables. It's actually table number 2, I think. Yep. So this is one way we do this. And of course, this is on hard paper. You can have a computer that does it general random numbers. So let's just say I have even 10 people and I want to pick 5, right? To make a simple sentence. So I just start anywhere and I go here, right? And I'm going to pick number 7. And then I'm going to have a pattern where I'm going to skip 2. So I'm going to pick number 6 rather. Number 3. So I'll pass that up and I'll move over and I'll pick number 4. And then I'll move to number 8. And I can do this any way I like. If I have 100 people to choose from, I can use the 2 numbers, right? So I can start here and pick number 21 and number 4, number 98, number 8, number 88, number 6, number 92, and go on until I get as number of people, right? But I'm just randomly picking. This is helping me to make a random choice out of that group of 100 people. And so I no longer have to, there's nothing in my choosing that can affect and bias the sample. Does that make sense, right? So we use tables of random numbers. And of course, there's computer programs to do this because we want 1,000 people, right? We're not doing 10 or 100. So, but this is the way it always worked in the past, way before when there was no computers. And this is a viable method. You can do whatever you want. And you could start anywhere. Like I could just as easily start here and say 21, 63, 87, 4, 61, 19, 18, 45, right? So this is just a tool you use to help relieve and eliminate or at least diminish bias, okay? So I'm going to stop sharing. Get back to my big head, all right? So that's using a table of random numbers, that's the way to go, right? And then there is the simple random sample, right? So if I wanted to use the class, if we were sitting there, I put your name in a hat and I just pulled names out of the hat, right? That would be a simple random sample. Then I could use what we call stratified random sampling, right? So subgroups of the population. So the population is somebody of Delta College. A subgroup would be the athletes. Another subgroup could be the English majors, psych major. We could divide everybody into subgroups by the major they've chosen or been assigned to. We can charge them by, you can do it any way you like, right? But let's be logical. In that situation, probably majors would be the best choice. Athletes versus non-athletes, you can do it by race, you can do it by gender, males and females. So there could be male, female, bisexuals, we could do it by any gender choice. Those are subgroups, right, of the population of the student body. So that's one way to do it. All right. So then what we can do what we call stratified random sampling. So once we have the subgroups, then we just randomly pick out of the subgroups to represent, right? So like I said, so if we want to represent all the different schools inside the Delta population, right? So everybody who's assigned to a major or whatever major they've chosen, then we pick out of those groups to represent the entire population of the school. Then there's what we call multi-stage random sampling, right? Which is more like what they did for the elections, right? So when we talk about we talk about the population in the United States, right? They're all voting for the presidency. Everybody's going to vote for the presidency, right? As opposed to congressmen or senators, right? Everybody has the same choice for president and the same choices. So now what we want to do is how do they poll that, right? I'm guessing you may have seen, like the polls say so-and-so's ahead, so-and-so's ahead, right? So what they do then is, let's say, so like in California, there's 58 counties, right? So if you take all the counties in the country and randomly pick some counties and then randomly pick some voting precincts, what they call is, right? There's different precincts, even in our county, like you were sent to vote in a particular spot, right? Anyway, however granulated you want to get about this, you could just go to every county and randomly pick some people, or you can break it down again to a next stage, which would be the voting precincts. and pick a certain number of people out of every precinct, randomly pick small number of people out of every precinct, poll those people, and then they represent the population of the country. And that's pretty much what they did. You can also stratify things like they do a lot, and you may get exposed to this later. When they give out money, when I was in the public sector and we were trying to get money, right? The state was going to give awards to counties, and the state broke us up by rural, urban, small, medium, and large, right? Or it could be rural, urban, and suburban, however you want to label it, right? But that's the way it was, right? And then the larger counties got a certain amount of money, and smaller counties got less because they needed to serve less people, theoretically. But you can do that, like if I want to find out, right? Because the people in the urban, the farmers have a different need than us that live in town. So if you want to get a population, a general sample of the population of San Joaquin County, you need to make sure you have farmers, town people, suburbanites, everybody, right, in there, from the little towns like Oakdale that live in the little town of Oakdale versus the farmers that live outside, right? Or those of us that live in a big city like Stockton, or what we like to call big city, or Lodi, right? So there's a lot of ways to stratify the choices to make sure you get a good sample of whatever the bigger population is. And then we have what we call cluster sampling. So in the book, I think it's Boy Scouts. So if you talk about the Boy Scouts, right, they're all over the country. So that's the population. I want to talk to all the Boy Scouts. So then a cluster would be a troop. Each individual troop of Boy Scouts would be a cluster. And then you would choose from the clusters. Or you could just choose the clusters. Right? I'm going to take a cluster from Dakota and Alabama and California and New York, and they're going to tell us and represent all of the Boy Scouts. Or I could just go to a larger number of clusters and take a few random people from those clusters, right? All right, the same thing. I would take all those clusters, throw them in a hat, and randomly pull a name out, and that's how I would do that. But that's how you would study a huge population like the Boy Scouts. You're not going to talk to every Boy Scout in the country, right? So that's sampling and how we do it and why we do it. Just some simple ways that we do it. Obviously, you know already there's samples that have hundreds of thousands of people in there, right? When we're talking about the polls for the vote for the presidency, they're not talking about 100 people. We're talking about a lot of people. When you're talking about all the Boy Scouts, you're talking about a lot of kids, right? And adults, I guess, now too. Anyway. All right, so as always, now we're going to transition into the next part of Unit 5, which is actually Chi-Square, right? We're going to talk about Chi-Square because what kind of fun would it be to have a unit without any math? And so this will be cut in, and I'll be in the classroom again doing the actual math part. But much easier, quicker, and this is it. So if you made it this far, you know, you got this down now, you're done. All right? All right, so we've transitioned back into the classroom because, of course, what kind of unit would it be if we didn't have math, right? So I know you were all looking forward to this. And remember, this is actually it. Like, this is the end, right? 2 weeks from now, 3 weeks from now, you'll be done. So, and this is much easier, this unit, like I said, is much easier than the last two that you got through. So if you're still here, this is really the downhill side, okay? So we're going to talk about chi-square. Chi-square is how we calculate data for nominal or ordinal data, right? It's how we manipulate nominal and ordinal data. So the simple one choice. I like candidate A or candidate B. I like vanilla or I like chocolate. I like textbook A, I like textbook B, right? One-way chi-square, there's only one choice. The options are only classified in one way. I hope that makes sense. Right? A or B. Okay? So, it's also called, so it's a one-way chi-square. It's also called the goodness to fit test. Right? Goodness of fit. We're also going to look at the two-way chi-square, right? So, because most data, even nominal and ordinal data, is classified in more than one way, and we'll get into that, right? But first, we're going to go with the one-way chi-square. So, I'm going to give you your key phrases, right? The key words. Chi-square. One-way chi-square. And two-way chi-square. All right, so here we go. One-way chi-square. Our data looks like this. Text A, text B, right? Text C. One choice, like out of this, one option. You like A, you like text B, or you like text C, right? So this is our table, basically. And we're going to have our observed values and what we call our expected values. Right? So basically, our expected values are what you would see. All right. So I'm going to go back and keep pumping this into you. The expected value is what you would expect to see if the null hypothesis is true. And there's no difference between the means. So whatever your number of subjects is, you just divide it by the number of categories, and that is your expected values. Right? So, we're going to say, I don't even know, oh, so in this case, I'm going to say N is 79. Right? This is a part in the book, so you can go back and look at it. N is equal to 79. So our expected values here is N over 3. You have 3 choices, right? So our expected value is 26.33. And it's the same in every category, right? It's the same for every option. And that's why I say this goes in line with the null hypothesis. Because the null hypothesis states there's no difference between the means. Okay? Now, however, we have our observed data. So out of these 79 people, right, they actually made their own choices. And they didn't go in line with the null hypothesis, and they had other choices, right? So what we're going to say is 30 people chose to like text A, 27 like text B, and 22 like text C. And these are the real values of the data we collected from the subjects, as opposed to the expected value, right? And here we go, real simple formula. Comparatively, x squared. So chi-square is x squared. Okay? And x squared is equal to the sum of our observed values minus our expected values. Oh, I better write that better, huh? They all my e's look the same, huh?
Yes.
They all look like the sum part.
Oh, that was an E?
Okay.
squared over the expected value. Much simpler than what we've been doing. However, the trick is you got to do the sums, you have to do this part of the formula for every option. Right? We want the total of all of these. So you have to do it for text A, right? And text B, well, let's do it. So we'll do it for text A, right? So we have our observed value of 30, right? Minus our expected value of 26.33 squared over our expected value of 26.33. I know it doesn't look like a 3, but it is. Okay? Just like that. So this ends up being 3.667 squared over 26.33, which is equal to 13.47 over 26.33, right? Which is equal to 0.511. Right? Much easier than the ANOVA, much easier than all of that stuff we've been doing, right? Same thing. So now we do text B, right? And our observed value is 27 minus 26.33 squared over 26.33. Same thing, right? We just plug in the other observed value. And here we end up with 0.667 squared over 26.33, which is equal to 0.445 over 26.33, which is equal to 0.017. All right, and now we'll just for textbook C, right? Same thing, nothing's changing. Minus 26.33 squared over 26.33, which is equal to negative 4.333 squared over 26.33, a lot of 0.33. Which is equal to 18.775 over 26.33, which is equal to 0.713. And now all I need to do, right, is the sum of all of this, right? So all I need to do is 0.511 plus 0.017 plus 0.713, and this is equal to, I'm going to put this here, right, just so you know, and this is equal to 1.24. So you're going to get the unedited version of this. So couldn't do what I wanted. Anyway, I'm going to go back. So right, so we have our sum. We have our value, right? As we've been doing, we're going to have to go back to the table, right? So like with all our other things, we need to know the degree of freedom, right? So for this particular model, the degree of freedom is the number of categories, whatever that may be, minus 1. Huh? Number of categories minus 1. So for us, there's 3 categories, right? And so the degree of freedom we're working with is 2. If you go to table 11, go to table 11, you go to the first column of degrees of freedom, you go down to 2, and you go across just like we have been doing to the 0.05 level and check the critical value. In our case, the critical value from the table is equal to 5.991. And obviously we are nowhere near that, and so we do not have statistical significance, and we do fail to reject the null hypothesis, right? One-way chi-square, very easy, right? Very simple. Much better than what we've been doing up until now, all right? So, as usual, we have our keywords of observed frequencies, right? Our observed frequencies, which is the data we collected. Our expected frequencies, which is just what you would expect if the null hypothesis was true, n divided by the number of categories, right? And then, of course, we have our observed values. I knew I could remember how to spell it. And our critical value. All the key terms. All right? That's one-way chi-square. Okay. All right. So, two-way chi-square, right? So the easy one-way chi-square, there was only basically one choice, one category. You chose one category, and the items were only categorized by one thing: text A, text B, by text C. But of course, life is not that simple all the time. So we have a two-way chi-square for when people are categorized in two or more ways, right? So medication trials. This is the thing. So we got a medication trial going on. We're giving some people, like they are right now, I guess, they're giving people the vaccine, right? There's the trials about the vaccine. So some people are getting a low dose, some people are getting a higher dose, and of course some people are getting a placebo to see how effective the medication is. And this is the way it's done most of the time, right? So for a two-way chi-square, you're going to set up a table that looks like this. For the observed frequencies of, this is three groups, right? So I have a low dose group, a sizable dose group, and then the placebo, right? So, and then people, so then this is what they got, and then this was the categories the second category they could be placed in, right, is they were either improved, they didn't improve, right? So we have three options here and two options here. And for this calculations, you need to set up these column totals in your tables and the row totals in your tables, and then the grand total is the totals of the rows, right? Okay. So these are the numbers you come up with. You add 20, 35, 44. Very simple. 24, 44. Nothing to that. You go down. 30, 14, 29, right? 29. Pretty simple, right? And then for the chi-square, the two-way chi-square, the formula remains the same. It's the sum of the observed frequencies minus the expected frequency squared over the expected frequency, okay? In this case, the expected frequency is, you need to stop this for a second. Okay, so these are our observed frequencies, right? And now we need to get our expected frequencies. And so, of course, obviously, with this more choices and more options and a more complex table is more complex, a little bit more work to do, right? Of course. So, our expected frequencies, right? For each expected frequency, you multiply the associated row total. So if I want to look at the improved column and the low dose, I'm going to look at the row total multiplied by the common total, the column total, right? So for my improved low dose, I'm going to go by the row column times the column total, right? And I am going to get, oh, that's what I needed because of my thing. And I am going to get 44, right, times 30 over the grand total. And this is how I'm going to get the expected frequency. Right? So it's the row total times the column total over the grand total. And that's the formula, all right? So this is it. So for the improved low dose people, large dose, sorry, I keep saying low dose. This is large dose and small dose. For the improved large dose people, this ends up to be 15. Okay? Now you got to do that for every category. So now we have, right, the improved small dose people, which turns out to be, right, 44 times 29 over 88, which is equal to 14.5. And we continue on. For the placebo people, right, the placebo improved, or the improved placebo, I guess, I gotta stay constant, right? For the improved placebo, right, it's 9. Oh, it's still the same. 44 times 29 over 88, which we already know is 14.5. Well, right? Okay. Now we have to do the not improved. Not improved large dose. Same thing. 44 times 30 over 88, not 18. So of course, this ends up all being the same because of course the author like set up the numbers to come out, right? So here we are again at 15, right? Same thing, not improved small dose, 44 times 29 over 88, which is 14.50, and the not improved placebo is 20, I'm sorry, right, is 44 times 29 over 88 again, which is 14.50. Right? So these are our expected frequencies for every column, right? So here's our observed, and this in turn would be our expected. So if I have this, right, my expected frequency for the improved large dose is 15, right? And I do the same, I can do the same for every box. Here it's 14.50, right? And here we have our observed and our expected, and this is again 14.5, right? And I can make adjustments to my table. Just so I can keep track of this. You don't have to do this, obviously. But I want to try to show you, demonstrate where things are. Okay? So here we go. We have now we have our observed values and our expected values, right? And so now we go back to here, right? And we go back to the same formula, right? And so now we have to do this formula for all of these options. So I'm going to erase this part, unfortunately, and do that. Back to the I'm sorry. Yeah. X squared is equal to the sum of the observed frequency minus the expected frequency squared over the expected frequency. Right? But now I have to do it for all 6 of these categories instead of the 3. That's all. Right? But it's still a simple computation. So now I have the improved low dose, right? Start in the same place, and I have the observed value of 20 minus the expected value of 15 squared over the expected value of 15, right? Which we all know is 5 over 15. 5 squared over 15, or 25 divided by 15, which is equal to, let's see, what is that equal to? 1.667. Okay? Now, I need to do my improved small dose, right? Same thing. So now I have my expected value, my observed value, minus my expected value, 14.50, right? Squared over my expected value of 14.50. Nothing to it, right? So this is equal to, we got 15 minus 1 squared, right? So it's 0.50 now, right? Squared over 14.50, which is equal to 0.250 over 14.50, which is equal to 0.017. And this is the same thing. We're going to do it for every box, okay? So, like I said, rather than go through all that over and over, this is what it looks like. I did that computation for every box, right? For every option: improved low dose, improved small dose, improved placebo, not improved low dose, large dose, not improved small dose, not improved placebo, right? And now my only goal is to sum them up. So basically I have 1.667 plus 0.017 plus 2.086. And then something's wrong here. Oh, here we go. Plus 1.667 plus 0.017 and 1.667. And of course, this worked out this way, but it doesn't always, right? And so my sum, right, or x squared is actually equal to 7.540. Okay? And we're going to do the same thing we've been doing. We're going to go to a table. We're going to go to the table 11 and do the same thing. So what we need, right, is our degree of freedom. And in this case, our degree of freedom is the number of rows times the number of columns minus 2. So your number of rows times your number of columns. So here we actually have 2 rows, right, and 3 columns, right? So it's 2 times 3 minus 2, or 4. Oh, I'm sorry. Nope, I screwed this up. And you're going to see it. All right. So, as always, to use the tables, we need to know our degree of freedom. And in this case, it's the number of rows minus 1 times the number of columns minus 1. So in our case, there's 2 rows, right, -1, and 3 columns, which is equal to 1 times 2, right, which is equal to 2. So you go to table 11, you look down the first column to number 2, and you move across to the 0.05 level. If that works, it's 0.03, right? And on and on. So we already know from our past thing, it was the degree of freedom was the same as our chi-square, one-way chi-square in this case, right? So we already know our critical value was, right, 5.991. Again, now with the two-way chi-square, our observed value is 7.540, greater than the observed value at the 0.05 level, so we have statistical significance, and we would reject the null hypothesis in this case. There you go. The two-way chi-square, okay? Those were our 2 biggies. A couple of minutes left, and we'll be done. All right, good. Okay, so just like we've been doing all along, right? We've been doing all this. The chi-squares tells us, specifically when we had our chi-square value of 7.540, that the variables had an effect on each other, right? So up until now, to measure the strength of that relationship, right, we use Pearson's R, right? And so, but for the chi-square, where we're using the nominal and ordinal data, we have a different test to tell us the strength of the relationship, and that is Cramer's phi. So this is basically the Pearson's R for the chi-square test. And the first thing you need to know is the range is all still from -1 to 1. If your answer is outside of that range, you know you miscalculated someplace. I emphasize this because with Pearson's R, people were still giving me numbers outside this range. If you get a number outside this range, you need to go back and redo your math. Okay? But it's basically going to tell us, just like Pearson's R did, the strength of the relationship between variables. And of course, there's a formula for that. Right? So, this little elongated O is actually called omega. It's the Greek letter. It doesn't matter. This is your symbol for Cramer's phi, right? And here's your formula: chi-square over n times k minus 1. In which case, of course, x squared is chi-square. N is the total number of cases, or our grand total, right? Here's the one. K is the number of categories for the variable with the smallest number of categories. Yeah, I know. And so let me tell you, this is on page 318 if you need to go back and revisit this, right? But we have the different categories, right? So the low dose, small dose, and placebo give us 3 categories, right, for the dosage. But on the other side, we only have improved and not improved. So there's only 2 categories. So in this case, in our case, K is 2 minus 1. K is 2. The number of categories with the smallest number of categories. In our case, that's the improved and not improved. All right. So we already have x squared up here, what that value is. We know that n, right, was equal to 88, right? And k is equal to 2. Okay? So here we go, we got it. We just plug in this up, right? So the square root of 7.540 over n times k minus 1. Okay? So, sorry. Might as well put this in. So 88 times 2 minus 1, right? All right? Which is equal to the square root of 0.0857, which is equal to 0.292. 0.27, and in our case, 0.29, right? So just like with Pearson's OR, this is the value you get, and this shows the strength of our relationship. So if you go back to your scale, right, we already know 0.29 is not a very strong relationship. There is a relationship. We know it's a positive relationship, but it's pretty weak because it's only like 20, right, third of the way to perfect.
Where are you going?
Okay? So, just like Pearson-Kramer's 5, this is the strength of our relationship for our chi-square on the medication evaluation. So, we're typically supposed to go over the median test at this point, but I'm going to bypass that. I'm going to I don't believe there's any questions on the exam about it, but there are some questions on the worksheet probably. So I will give you the credit on the worksheet. If there isn't a question on the exam, I'll take a look. Anyway, if there's any questions on the median, I will, as a bonus, I'll give you the credit just for hanging in there. Okay? So you don't have to worry about that, but unfortunately I don't think there is much there. But it could be something. Anyway, this is it. You made it. Congratulations, and I hope you got something out of all of this. You hung in there. I know statistics isn't everybody's favorite, but at least now you can move on to whatever it is you plan on doing next. So good luck. Thank you.